Hi there, this is Courtney and Emmy, and this is our presentation on Chapter 2, which handles the manifestation of uniform random numbers. So the first thing we see in Chapter 2 is this concept of linear congruential generators. And so what these generators do, they deliver a sequence of non-negative integers where our x sub I is going to equal a times x sub I minus 1 plus c times mod m. And so it also uses the following parameters, which we saw up here. So a is the multiplier, x sub 0 is going to be our seed, so that's our initial thing we're starting with. Then c is going to be our increment, and then mod m, that returns the remainder after dividing the multiplier times x sub I minus 1 plus c by m. And so the number that's going to be generated is going to be r sub I, which equals x sub I divided by m. And so the objective is that we're looking to see if m is large enough so that the discrete values here, so anything m minus 1 over m, are close enough together so that r sub I can be treated actually as a continuous distributed random variable. So for an example, let's say that our multiplier is 9, our increment is 3, and our m is 2 to the power 4. And so we're going to choose to have this interval of 0 to 15. So we'll have our seed be 3. So if we were to plug that in to start with 3, then x1 would equal 30 mod 2 to the 4th, which comes to 14. x2 would be 129 mod 2 to the 4th, which equals 1. So then so on and so on, we would get this sequence that's written out right here. And so one of the things we're looking at with a generator is the period of it. And so it's basically the smallest integer lambda such that x sub lambda equals x sub o. And so in our example, this sequence repeats on the 17th number right here. So in the beginning, it's 3 over 16. At the end right here, it's 3 over 16. And if we were to keep going, we would see 14 over 16, 1 over 16. And so our lambda equals 16. The objective is to make the period as large as possible to avoid this repeat, but the period cannot exceed m, so usually the modulus is chosen to be that largest number. So then the next thing in Chapter 2, it's mixed linear congruential generators. And so this is the case where the increment is always greater than 0, and our m is 2 to the power of b, where b is going to be the max number of bits that a computer language combination has. And so typically we're dealing with 32 or 64 bits. The 32-bit one is going to be more common in these just because it's a little bit faster, but the 64-bit is used to avoid overflow. But because it's doubled up, it's typically slower than the single precision one. And so if you look down here, that we see that computers often store integers in this interval, which is -2 raised to the 31, 2 to the 31, and -1. And so 1 bit is usually reserved for this negative sign here, so that's why we don't get the 32. We're using 31. And so, like I mentioned above, using that 64-bit, since it's doubled up, it's a little bit slower. We could use this method down here to avoid that overflow as well.
So another type of linear congruential generator is the multiplicative one. This is when we set our increment, or our c, equal to 0. Obviously, when we look at the equation that we've set before, the algorithm, with our c equal to 0, our algorithm now becomes the x sub I equals a times x sub I minus 1 mod m, because that plus c that used to be in there is now 0, so it becomes multiplicative, which means that, again, there is no more c in that algorithm. This has some conditions with it, though. Your initial x sub I cannot be 0, and your period cannot exceed your m minus 1. So one of the things that if you want to achieve a maximum period, is if and only if m is prime and a is a primitive root of m. So when you're matching these conditions, we call this a maximum period prime modulus generator. So what are some theoretical tests for random numbers? Some of those linear congruential generators fall to basically one of 3 types, where lambda is a period. So in the first type, we call it a full period multiplicative. It's where we set our m equal to 2 raised to the power of b. We've seen this when we looked at a 32-bit system in the beginning. We set that as 2 raised to the power of 32 or 2 raised to the power of 31 minus 1 sometimes. Anyways, continuing on, we set a equal to 1 mod 4, and c has to be an odd value with lambda equal to m. In other words, the period has to be equal to m. Now in the second type, type b, this is the one we just looked at, which was a maximum period multiplicative prime modulus. Now this is where m is a prime number and a equals a primitive root of m. C, again, it has to be 0 because it's multiplicative, and our period is m minus 1. And the last type is what we call type C. This is where you get a maximum period multiplicative. Again, we set our m equal to 2 raised to the power of b, a equals to 5 mod 8, and lambda is 1/4 of m. Now, as you've kind of seen, is these three theoretical tests, or the three tests that we've kind of looked at, use the values of a, c, and m to assess the quality of the output of the generator over the entire period. As you can tell above, m, a, and c are typically different, and what they'll get is a different period. Now, investigating the lattice of a generator. So investigating the lattice of a generator really just gives us deeper insight into the quality of a generator, and what it ends up doing is investigates the independence between randomly generated pairs. So it wants to make sure that when looking at randomly generated numbers, that we're not having redundancies, trends, or anything of that liking, even though they may be randomly generated. In other words, or they would not have they would have a large period. They can still show that there is a trend in it. So what you want to do is you want to make sure that when they're plotted, the pairs should be uniformly distributed over your period. So the last thing we want to talk about is some of the problems with increasing your dimensions. So what we want to talk about a little bit is graininess of a sequence. And what that is when you look at the average distance of a two-tuple to its nearest neighbor. So generally speaking, in order to generate a point uniformly distributed over the period of 0 to 1 squared, we would usually take two consecutive random numbers, and there are m minus 1 such two tuples. And you want to look at the average distance to its nearest neighbor. And really what you look at is, in developing its average distance to its neighbor, it's approximately 1 over the square root of m. So now if we take that to the kth degree, in k dimensions, the corresponding distance is approximately 1 over the kth root of m, which is 2 raised to the negative b over k. So if we use an example to set b equal to 32, typically a 32-bit system, and an integral of 8 dimensions, the average distance you would look at is, if you can set this up, 2 raised to the power of negative 32, which is your your b, over 8, which is your k, or your dimensions. And you have to come up with 1 over 16. This 1 over 16 gives us the average distance to its nearest neighbor of the tuple, or the approximation to it. Now, if we continue to raise the dimensions, in other words, take 8, and let's say push it to infinity, just for absurdity's sake, we would actually notice that the average distance to the nearest neighbor approaches 1. So how do we mitigate this factor? So to mitigate the effect of the increasing of the dimensions, we can shuffle the output in order that the number possible k tuples is much greater than m minus 1 that's available in the unshuffled sequence. The other thing is to use Tausworth's generators, and the last one is combining generators. So I hope you've enjoyed this. And thank you for watching.